All right, do we have any questions about limiting reagents or any stoichiometry from last time? Did we practice that and get stuck somewhere? Now would be a good time to go over that. We can go over a sample question. How are we feeling?
Let's go over a sample question.
Sounds good. Does it bother you that I ask you so many questions in here? Okay. Okay, on the worksheet, did you want to go over any of those? Anything in particular? Should I just pick one? Pick one? All right. Let's do number 3. So it says, we have an equation, 4Al2O3 plus 9Fe gives us 3Fe3O4 plus 8Al. Okay, we can't do any of this without a balanced equation, but we have one right there. So it says if we have 25 grams of this, of aluminum oxide, and 10.2 grams of iron, we want to determine the limiting reagent. What's another name for limiting reagent? Limiting reactant, right? Okay. So how do we do this? We start with what we know, and what are we going for? It doesn't tell us. It just says, what is the limiting reactant for part A on number 3?
So it's whichever,
We just need to find one what? One product. Any product. It doesn't matter which one. Okay? So before we just pick one, let's look at letter B, part B on this. It says determine the number of moles of aluminum produced. So what product should we choose? Aluminum, so we don't have to do more than we have to, right? I mean, you can, it's extra practice, no big deal. So let's just go, let's find out how many grams. Well, in part B it just says moles. Can we just go to moles? Moles of aluminum, that's what we're looking for. Are we okay with that? Okay. So where do we start? 25 grams or 10.2 grams? Because we're given both. Either one. It doesn't matter. We've got to do both of them. Right? So let's convert 25 grams of what?
aluminum oxide.
Good, aluminum oxide. Write it out. And we got to convert that to moles of aluminum. Do we want grams of aluminum oxide in our answer? If we don't, then where does it go? On the bottom of our conversion factor. So grams of Al2O3. And what do we know how to convert to? If we look at our mole roadmap, what can we convert to? Moles. Yeah. If we have 1 mole of Al2O3, we can find the molar mass of aluminum oxide. Aluminum is 27, is that right? Look at our periodic table. Don't try to memorize this because we have a periodic table to use. Let's use it. But I believe it's 27, about 26.9-ish. So 27 times 2, that's 54. And tell me if I'm wrong, because I'm just going by memory. I hope you guys don't just go by memory. Okay? And oxygen is 16 times 3, that's 48. Am I right? Okay. So that's 100 and what? 2. 102 grams per mole. So that 102 goes right there. So we can change colors. And grams of aluminum oxide go away. Now we're at moles of aluminum oxide. That's not what we're looking for. We're looking for moles of aluminum. So we keep going. What goes on the bottom? Moles of aluminum oxide. So they cancel. You with me? Any questions so far? Can you do this on your own yet? Okay. Make sure you can before we leave tonight-ish. All right. So we can convert moles of aluminum oxide to what? Can we convert it to moles of aluminum yet? If you look at our mole roadmap, can we go from moles of one substance to moles of another substance? Yes, we can. So if you forget what you can convert to, watch that map, okay? So how many moles of aluminum to how many moles of aluminum oxide? Yeah, what's the mole ratio? How many moles of aluminum do we put in there? What? 8. Right? This number right here. Yeah, yes, you can simplify it in your head if you want. But if you do, you better be right. I'm just going to use the number that's on the balanced equation. We've got 8, because will our calculator simplify it for us? Yeah, they'll figure all that stuff out. But yes, you could do that, Peter. No problem. So the question was asked, can we simplify, since we see it's an 8-to-4 ratio, can we just say it's a 2-to-1 ratio? Yes, we could. But why take the chance? I mean, they are small numbers, and yeah, that's right. So that's going to be 4 because of that number right there. Any questions? Can we all do this? Good. So that goes away, and that's what we're looking for, moles of aluminum, so we're done. So 25 divide 102, multiply 8, divide 4. Or yes, we could just multiply by 2 because we can see that 8 divide 4 is 2. That's fine too, no problem. What do we get? Somebody? Start with 25. Divide 102 because it's on the numerator. Or on the denominator, sorry. What? 0.49? Do I have a second? All right, okay. 0.49 moles of aluminum. Is that my answer? Oh, if we're not sure if that's our answer, we should go back to the question. What does the question ask?
What is the lowest or least?
What's the limiting reagent? Yeah. So is that our answer?
Possibly, we have to do the other one.
Absolutely not. That's not our answer. It possibly could be that, but we got to check to see if it's that, right? So we got to check one more. So let's do it. We start with 10.2 grams of iron. And we're going to do the same thing, grams to moles, right? So what's the molar mass of iron? Is it 56-ish? 55.8 grams of iron to 1 mole of iron. I'm going to have to take a quick break. Why don't you guys finish this one? I did one, and I did the harder one. All right. So we can see that grams of iron go away. And what's the mole-to-mole ratio from moles of iron on bottom, so it can cancel?
Hold on the screen.
Uh-oh. Thank you. Yes. All right. What are we going to convert to? Moles of what? It better be the same thing. Otherwise, we cannot compare them. Okay? You have to go to the same product. Does it matter which product you choose? No, but once you pick one, stick with it. So this is moles of aluminum, and what's the ratio? What goes on top? 8.
Wait, so why is it aluminum on the top?
The same reason why it's aluminum here. Why did we choose aluminum? We could have easily chose iron, what is that?
But we can't compare the top equation with the bottom equation.
If they're not the same.
Right.
Yep. Did that answer your question?
Yes.
Anybody else? Okay, what goes on bottom? 9. Okay. That goes away. Then we'll do 10.2 divided by 55.8, multiply 8, divide 9. What do we get? 0.16. Do I have a second person that got that? Okay, good. 0.16 moles of aluminum. Always check your answer. Do it twice. Sometimes we can make a mistake on our calculator. Push the wrong button. Easy to do. So double check it. All right. Which one is our limiting reagent? Iron is. Why is it iron? Because it limits how much aluminum we can make. It's a smaller amount, right? Everybody get that idea? Questions? Okay. So the answer for part A is iron is the limiting reagent or reactant. Okay. Who can tell me what the excess reactant is? Aluminum oxide, the other reactant, right? Okay, good. And then part B asks, or it says, determine the number of moles of aluminum produced. Now, this is just a prediction, right? What is our best prediction here? Is it this one or is it that one? It's 0.16. It's the one produced from our limiting reactant, right? Okay. We're never going to use this one. Never. We can cancel that. Don't even use that. So our answer for part B is 0.16 moles of aluminum. We got part B from part A. Don't have to redo anything. Unless we decided to find out how many grams of aluminum, right? Because we could have done the same thing with converting it to grams, and then we would just have to cross off the last conversion factor to find out how many moles, right? That's it. Okay, and then part C says determine the number of grams of excess reagent left over in the reaction. So our excess reagent is Al2O3. We want to know how many grams of this we have left over, right? Okay, so where do we begin? Go ahead.
25 grams.
25 grams of aluminum oxide? What do you guys think? We start there?
Well, we can
Are we going to use all of that? We're not. We know we have some left over. Does everybody get that? We know we have leftovers. We want to know how much we have left. So to do that, we have to know how much aluminum oxide we actually react with iron. So we found the limiting reagent for a lot of reasons, to find out how much aluminum we can make, how much iron Fe3O4 we can make, and also how much aluminum oxide we need. We always use the limiting reagent. That's why that's the first question. And we move on. Now, in real life, no one's going to ask us what the limiting reagent is. That's just something we got to find out so that we can know what the answer is, right? In the end, part B and part C is the only thing we want to know. So let's start with what we're given. We have 10.2 grams of our limiting reactant. Okay, so we're going to start there. Any questions on why we start there? Good? And we're going to convert this to what? No, in the end, what are we going to convert to? What's our end goal?
How much aluminum is left over?
Grams of aluminum oxide. Yeah, that's it. We're looking for grams of aluminum oxide. So we can convert until we're there. So we're just going to copy and paste this guy right there, right? Whoops. 1 mole of iron for every 55.8 grams of iron. That goes away. And then we use the equation. It's an 8-to-4 ratio. Uh-oh. I'm not going from aluminum. Iron. 9-to-4 ratio. So we have 9 moles of iron to 4 moles of Al2O3. Questions? Why I did that? We okay? So moles of iron go away. And now we got to convert moles of aluminum oxide to grams of aluminum oxide. So 1 mole of Al2O3 has a mass, and we don't have to redo this because we just have it up there. 102 grams of Al2O3. That goes away. We're left with grams of Al2O3, so we can find our answer here. 10.2 divide 55.8, multiply 4, divide 9, multiply 102. And what do we get? $8.2? 8.286?
So we rounded up to 8.29.
8.29, yep. And that's going to be grams of Al2O3. Is that our answer? No, it's not. That's how much. What is that answer? What does that mean? Yeah, that's how much we use, right? How much did we start with? 25 grams. So we start with 25 grams and we use 8.29 grams, and that leaves us with how much left over? 25 subtract 8.29. I don't like to do that one in my head. What is it? Maybe. 15.71?
Oh, that's a 9, sorry.
So is it 15.7?
16.7.
16? Okay.
Yeah, that's correct.
16.7
One.
grams of aluminum oxide left. So make sure you read that question because we did a lot of work. By the time we're done with that work, we want to just circle our answer, right? Don't make that mistake. Go back to the question. What is the question asking? Make sure you've answered it correctly. Good? How are we feeling? Feel like we can do these yet? Okay. Try to get that Unit 3 test done by this weekend, next week, this upcoming weekend. Okay? Try not to delay it past that point. Because, I mean, we're moving on today, regardless, so. Anybody take it already? All right, good. All right. Any other questions or concerns? Okay, let's move on to today's topic, which is balancing equations. And like I mentioned earlier, we could get done early, or if it's hard and you guys there's a whole page. If you guys picked up this sheet, has all the answers on the back. But if you practice this without looking at the answers and check your answers, and guess who makes the answer key? Not me, but a person does. So could the answers be wrong ever? They could. They could. I just got this from the internet. Okay? They could be wrong. So if you're wondering on one, bring it the next time and we'll look at it. Okay? But practice those. All right. So I'm going to do a little bit of review on chemical equations. And let's use an example. And we already did this one, but let's do it again because I like how it's set up. All right, who can tell me what the guys on the left are called?
The reactants?
Reactants. These guys react together, right? And what do you call the guys on the right?
Reactions.
The whole thing is a reaction. What do we call the guys on the right? The reactants make the products or produce the products, right? Do we get that? And this arrow right here means, well, it makes, yields, produces, whatever. Are we good? And these guys right here are what? That's the state of matter, right? Solid, liquid, gas. And what's this one over here? AQ?
Water, please.
Water solution, where water's a solvent, right? It's an aqueous solution, hence AQ. That means NaOH is the solute, right? Are we good? Do we understand a basic chemical reaction layout? What everything means? All right. Let's start with one of the simplest equations. So balancing equation, a balanced equation. What does that mean? We kind of talked about it last time, but I want to give you a whole definition. What is a balanced equation? I don't know, just tell us, right? A balanced equation, well, what does balanced mean? Same on both sides, right? Like a scale, okay? Same amount of each element on each side. Okay? And so, like we talked about in limiting reagent or just stoichiometry in general, we have to have a balanced equation. Otherwise, we can't make cookies, right? Got to have that recipe, not just the ingredient list. If you have an ingredient list of cookies, can you make very good cookies? No, you might have too much flour or too much sugar or too much salt or whatever, right? I don't know if you can have too much chocolate chips, but whatever. Okay. But you can't have not enough. So let's do an example. We have H2 plus O2. What do you think it makes? Water, right? But we can see that's not balanced. So you can do this a few different ways. I'm gonna show you how to show work. A lot of people like this. Some people don't. But you do it the way that works for you, okay? So I write a line right where that arrow is. On the left side of the arrow, I have hydrogens and oxygens. On the right side of the arrow, I better have the same ones. If I don't, something is wrong with my product, right? I can't start with hydrogen and oxygen and end up with something different. Got to have the same elements, okay? And so let's just count these. On the left side, how many hydrogens do we have?
2.
Yeah, that means we have 2 H's, right? Are we okay with that? How many do we have on the right side? Also 2, right there. Good. How many oxygens do we have on the left side?
1.
2.
Look again. It's O2.
Oh, left side.
Yeah, the left side. We have 2. How many do we have on the right?
1.
1. So oxygens are not balanced. So how do we balance these equations? By adding coefficients. And what are coefficients? If we have 3x, what's the coefficient of x? 3, right? 3 is the coefficient of x, the number out in front. What are the coefficients in our balanced equation right now?
2 and 2.
There are not any coefficients, so what do we call the coefficients? 1, right? If I write x, I know that's 1x, right? Same thing here. I have 1 H2, 1 O2, and 1 water. You with me? But so far this isn't balanced, so we've got to add coefficients to make it balanced. So let's start with oxygen, because oxygen is the only one that's not balanced. If there's 2 on this side, we should try to have 2 on the other side. How do we do that? By placing a 2 right there. You with me? But what does that do? That makes so that we have 2 waters, and every water has 1 oxygen. If we have 2 waters, that means we have 2 oxygens. You with me? What does it do to the hydrogens? Yeah, 2 multiply 2, because every water we have 2. Well, we have 2 waters, that means we have 4, right? 2 times 2, that gives us 4. Okay, oxygen's good, but now hydrogen's not good. So let's go back to the other side, see if we can change something. Where should we put a coefficient? In front of hydrogen, what should it be? 2. If we put a 2 there, that changes this into 4. We got 4 here, 2 there. We're good. Does that make sense? That's the simplest equation we'll ever see. And just keep going back and forth until it's done. Now you can do that with every single equation on this worksheet. Every single equation you'll ever see. And you should be able to balance it. I'm going to show you a few tips and tricks to make things a little bit easier. Sometimes they get a little bit tricky. Okay? Again, if you don't memorize these tips and tricks and you forget them, you still should be able to do it. Just keep going back and forth until you get it. Okay? And sometimes it feels like you're pulling your hair out trying to get this, and it doesn't feel like it's even possible. And that's why the tips and tricks are very useful. Okay? Do you want me to give you the whole list of tips and tricks, or just one at a time and then do an example? Maybe that would be easier, right?
One at a time and do an example.
Okay, so I'm going to leave some space, and you guys should do the same, to make a list of tips and tricks. Okay, first one. And I always start with this one because if you do this one, it's probably going to help you the most, okay? And when I say the most, for most equations, okay? And again, if you don't do this, it doesn't mean you won't be able to balance it. You still will. It just take longer, and you're going to have to use your eraser and start over. But let's just do this. So we got begin with largest number of atoms. Any ideas why we would start with the largest number? Because it's easier to make the little ones bigger rather than the bigger ones smaller, right? How do you make a bigger one smaller? Put a half in front of it? Can we have half of a particle, half of a molecule, half of an atom? We cannot. So that's why we start with the biggest numbers. So I'm going to leave, let's do 1, 2, 3, 4, 5, 6 tips and tricks. And some of them are longer than others, so if you want to have 2 lines per tip and trick, just always give yourself room, okay? Even when you write regular notes, don't just cram all your notes in, because those aren't fun to read. All right, let's go to our first example, second example. Okay, if we have carbon dioxide plus oxygen, plus water, and we get C6H12O6, which is glucose and oxygen. Anybody know what this is? This is photosynthesis. You guys ever learn about photosynthesis? Okay, that's all this is. And if you flip it around, then it's what? Respiration, right? Okay. You don't have to know that for this class, but here we go. All right, so do you guys like showing your work? Does that help? Then do it. Okay, so we have carbon, oxygen, and hydrogen on each side. Okay? Which compound should we start with? Carbon? That's an element. Which compound should we start with? Carbon dioxide? Should we start with carbon dioxide? What do you think? if we're following this tip, begin with the largest number of atoms. Which one has the largest number of atoms? C6H12O6, glucose, right? Let's start there. And don't get me wrong, you can start at CO2, no problem. But you just might have to go back and forth more times. That's all, okay? So let's start with carbon here. We have 6 on this side. And rather than writing 1 on this side, because I know I'm going to change it, right? And if you guys want to write 1 and then cross it out and then write the next, okay? You can. What coefficient should I put right here to make so there is 6?
6?
6. Does that make sense to everybody? It just saves you a little bit of time canceling and erasing and all that stuff. You okay? And when I do these, I don't show all of this work. I just go back and forth until it's all done. You do what feels good for you, what makes sense to you, okay? All right, next let's go with hydrogen. We have how many on the right side?
12.
12. How many on the left side? 2. So what coefficient goes in front of water? 6 to make 12. You get that? Okay. And then last, I put it under an oxygen. That's 12 hydrogens. Okay, now let's do oxygen. Which side should I count first? There's oxygens everywhere. And that's actually another tip and trick. Save that one for last. Otherwise, you're gonna pull your hair out, okay? So maybe we should write that one in there because we're actually doing it. If an element appears did I spell it? Is there only one P?
2 P's.
Okay, thank you. If an element appears more than once on a single side of the equation, save for last. And would you be able to do it if you didn't save it for last? Yeah, in some cases, it's actually the best one to start with, but most of the time it's not, okay? So this is just a good rule of thumb. Are we good? Ready to move on? Not yet? Moving on? Okay. So which side should we start counting the oxygens on? Left or right? Why left? Because, well, there are more because we have the coefficients already set in place, right? They're set in place. We don't have to, hopefully we don't have to change those. They're already balanced. So let's count this side. So here we have how many? 12, 6 multiply 2, right? Are we good with that? And over here we have how many? 6. So we have a total of 18. Questions on that? Okay. Over here, hopefully we don't have to change this one, because if we do, we have to change them all, because we started with that, right? How many oxygens do we have here? 6 plus what
2.
makes 18? 12. That means there should be 12 oxygens here. What coefficient goes there to make 12? 6. Do you get that question?
Oh.
Does that make sense?
It doesn't, but it's because we skipped ahead.
We could have put a 2 here. We could have. And says we have 8. Okay, we need 10 more. It's hard to know where the 10 goes if we don't do it the way that I did it. Do we put some on this side and some on this side? Right? And that's why I did it. Go ahead, question.
So do you put, or is it possible to put some on one side and some on the other? Is that what we should do for any of them?
If we change this number, if we put a number in front of this big compound, we're going to have to change everything.
Right.
So let's try not to.
Oh, okay.
And besides, this oxygen is all by itself. If we could put whatever number we want, and what does it change? Just the oxygens, right? So that's another little tip and trick. Let's write that down. If element is all alone, save for last. That way, we can change that one and it won't affect anything else. Does that make sense? Do I need to go back? If element is all alone, save for last. All right. So now we have 18. Because we put a 6 there, and that makes 12, right? We have a total of 18. Everything's done. All balanced. Okay? A little bit more complex, but not too bad if you just go back and forth and follow these little tips and tricks. Okay? Questions on that one? Let's do probably the hardest one. This one kind of has a bunch all together, okay? Or do we want to practice some of these on our own real quick? How we feeling?
Let's do an on our own little thing.
Okay, go ahead. You could pick anyone you want on here. And the bad thing about practicing one on your own is you might end up with doing one like this that I'm going to show you next. But go ahead, try it. Try number 1, then 2, then 3, then 4. So if you feel like this is easy, yeah, just keep going. Get the practice. Make sure it is easy or that you are good at it. The answers are on the back, but try not to look at the answers until you're all done. Just take a few minutes to practice these.
Would it be possible just to go through one?
Just one?
Mm-hmm.
Which one?
First one.
Wait till I show you a little trick on that.
Okay.
Okay? I decided to do a different one than what I was going to do first. I'll do another example here, just to show you one of the other tricks. All right, so let's say, here's another example. Let's say we have iron reacts with oxygen to produce iron 2 oxide, or iron 3 oxide, which is rust. Okay. If you see that there's an even amount of an element on one side and an odd amount of that same element on the other side, here's a little tip. Let's give you this tip. If even amount on one side and odd amount on other side, then use least common multiple. You guys remember what least common multiple is? So what's the least common multiple of 2 and 3?
1?
Is that the right word? Is the not the least common factor, least common multiple. They both multiply into what number evenly? 6. Is that the right word, least common multiple?
No, it's factor. He said it was factor.
Least common factor is like 1.
Oh.
The least common, that is least common multiple, right? That's least common. So that's for fractions. Okay. Okay, that's what yeah. All right. All right, so, and again, we can show our work here. We have iron and oxygen on both sides. The least common multiple of 2 and 3 is 6, right? They both go into 6 evenly. So we're going to make this be 6. And what coefficient do we put in front of oxygen? 3, right? And what do we put in front of Fe2O3 to make 6 oxygens over here? 2. So you pretty much just swap them, right? Okay. All right, and we do that, and we get 6 on the left and 6 on the right. Are we good? And then irons, where should we count first, left or right?
Right.
On the right side, how many?
4.
We have 4 on the right. So what do we put right here to make so that we have 4? 4. And we're good. Not too bad, right?
Mm-hmm.
That little trick, I mean, what you generally do is maybe start with iron, and you have 2 on one side, you put a 2 in front on the other side, and then you look at oxygen, it's like, that's not going to work. Another thing to do is, rather than, if you don't like using least common multiple because that's mathy, you look at this guy, say, all right, this is odd, and this is even. This side's always going to be even no matter what we put right there. This side's going to be odd unless we put what in front of it? A 2 always makes it even, right?
Yeah.
Okay? That's another way to look at it. Same idea, same thing. Get the same result. Any questions on that one?
Could you go back up to the,
Yep, sure can. Yep. Anybody else need this up still? So that might be good to have on your reference sheet. Or if you practice the heck out of these, maybe you'll just get good at it. Okay? All right, let's do another example. Example 4. So we have Si2H3 plus oxygen, which is O2, gives us SiO2 silicon dioxide, and H2O3. All right. This one, let's just start with the tip. Oops, let's use the right color. If we can balance the equation using fractions as the coefficients, then do it. Can we leave it as fractions? We cannot. So once we finish, just multiply. Oh, that was weird. Multiply everything by the smallest whole number that makes them all whole numbers. Okay? I'll show you what this means. So if you can balance the equation using fractions, then do it. When you're done, when it's all balanced with a fraction, then multiply all the coefficients in the whole equation by the same small whole number to make them all whole numbers. And an example says 1,000 words, so let's do that next. Who needs this screen up still? No? Okay. All right, so let's just balance this like normal. All right, where's a good place to start? What compound should we start with? That's an element. We should either start with this one or this one, right? Those are the largest numbers. So let's start with the left because that's how we read. Okay? So we have silicon, hydrogen, and oxygen. So you want to start with hydrogen? It only appears once on each side, so that's a good place to start. We have 3 on the left and 2 on the right. Oh, we know how to do this. What do? Least common multiple, right? So we're going to put a 2 right there and a 3 right there. So did you notice that? Is that why you said hydrogen?
Yeah.
Yeah, nice. Great. So if you know these tips and tricks and you can recognize that, it saves you a bunch of time, okay? But it's just time. You should still be able to do this. Don't be afraid if you don't remember all these. Okay, so we have 6 hydrogens on both sides. Okay, so now let's just count the silicons because we changed that one already. Silicons, there's how many on the left side? 4. How many on the right side? 1. So what do we got to put? 4. A 4, right? Good. So far, we're all balanced. Now we just deal with the oxygen. Good, because that's all by itself, and it appears twice on the other side. It's a good one to leave for the last. So let's count the right side because it's already balanced. We got 8 in this compound and 9 in this compound. That's a total of 17. So what number goes right there to make sure we have 17? What multiplied by 2 is going to give us 17?
8.5.
17 halves, right? Or 8.5. Your call, right? I like to do fractions because, well, if you multiply that 2, it makes 17, right? And it's easier to see what to do next. So now we have 17. It's all balanced. But we don't want to leave that like that. You can't have a half an oxygen molecule, right? So what are we going to multiply everything by? How do we get rid of that denominator, that fraction?
Multiply by 2.
Multiply this one by 2. If we multiply this one by 2, let's multiply all of them by 2. Will it still be balanced if we multiply everything by 2?
Yes.
Yeah, that's the rule of algebra, isn't it? Whatever you do to one side, do to the other side, so it remains equal. So we multiply that one by 2, multiply this one by 2, we get 4 here, we get 8 here, and we get 6 here. And we could even count again if we're not sure. 4 times 2, that's 8 silicons, 8 silicons. 4 times 3, that's 12 hydrogens. 6 times 2, that's 12 hydrogens. 17 times 2, that's 34 oxygens. And we get 8 times 2, that's 16 right here. 6 times 3, that's 18 right there. What's 18 and 16 make? 34. Still balanced. Do we get that? That's probably the hardest one. Yeah.
Where did you get the 17 over 2?
Because, good. So over here I counted 17. Remember that part? And I know something times 2 has to equal 17. Do you understand that? Divide 2 to both sides, and you got x equals 17 halves. Good question. Any other questions that you just didn't see what I did?
So it's just best to leave it in the fraction so you can multiply everything.
I like to, because then I can see what I have to multiply by. But if you know it's a half, it's also 2, right? It doesn't matter. It really doesn't. But I like to use fractions because it's easy for me to see. That's me. Okay? Are we good with that? We have one more example, then we're done. Unless you guys have questions, and then we can go over, after this next example, we can go over number 1. Or you should be able to do number 1. A little bit easier.
When you answered the, use least common multiple, that answered most of my questions for 1, but,
Okay.
I think we should still try.
Yeah, let's do it. Well, let's do another example first. Let's do our example 5. So let's say we have Fe2SO4 in parentheses and 3. What's that called? Iron 3 sulfate, right? Plus potassium hydroxide gives us potassium sulfate and iron 3 oxide, hydroxide. Okay. Iron 3 hydroxide, yeah. All right, so let's balance this thing. We got irons, and here's our trick. Let's write our trick real quick here. Our last one. If we have the same polyatomic. You guys remember polyatomics? We have the same polyatomic on both sides. Then we can treat it as a single unit. So we have sulfate, on both sides, we could just count how many sulfates we have rather than all the S's and all the O's. Saves a lot of time. So again, if we have the same polyatomic on both sides of the equation, then treat the polyatomic as a single unit. Does that make sense in your mind? If it doesn't, we'll do an example. Can I move on? Or not yet? Good? All right. So we have iron, and here we see we have sulfate on both sides, SO4, right? So I'm going to just count the SO4s. And potassiums, and I have hydroxide on the same, on both on each, or both, each on, hydroxide on each side, sorry. All right, so on the other side we have iron, SO4, potassium, and hydroxide. And ladies and gentlemen, if you want to just count every element singly, you'll still be able to do it, okay? You still can. This is just something that helps you do it quicker. Or maybe with less stress, okay? All right, so let's do, where should we start? Iron? Is that what you said? Where's a good place to start using our tips and tricks? Either here, right? We have 3. Or should we start at 4?
Shouldn't we start with the ones that are different?
3.
What do you mean the ones that are different?
Like K2 and, or FE?
Yeah, we're going to eventually do those. If you start with the largest number, then you make everything rise up, right? It's a lot harder to bring things down without using fractions. So I'm just going to start with sulfate here because there's 3 of them. I'm not going to start with 4 because how many sulfates are there?
1.
Just 1. Okay? So there's 3 sulfates on the left. There's only 1 on the right. So what number goes in front of K2SO4? A 3.
9.
Not 9. We have 3. Does that make sense?
Yeah.
3 sulfates. There's 1 sulfate in that compound. So if we have 3 compounds, we're going to have 3 sulfates. You with me? Okay. And then since we changed this, now let's do potassium. How many potassiums do I have on the right? 6. How many do I have on the left? 1. So I better put a 6 here. Now I just changed the hydroxides. How many hydroxides do I have on the left? 6 on the left. How many do I have on the right? 3. So I better put a 2 here. That makes 6 there. I have 2 irons here. How many do I have on the left?
2.
Also 2. Oh, not too bad, right? No. Yeah, there are multiple ways to do this. Did you get it right?
Yeah, I think
No problem.
3, 18, 9, 6.
Yeah. You see, there's more than one way to do these. The way I'm showing you is not, you have to, I hate when teachers say, you got to do it my way. It's my way or the highway. You guys ever have math teachers that tell you to do that? My way or the highway. I know they're trying to teach you a concept, but if you can do it, why not, right? So, yeah, there's tons of different ways to do these. I'm just showing you little tricks to maybe make it easier. I'm sure if when you do this practice, there's going to be one that's you're going to start pulling your hair out. Don't pull your hair out. Go to the tips and tricks. In fact, if you ever feel like you can't figure it out, erase it all and start over. Okay? Start somewhere else this time. So, should we do number 1 on this?
I don't want to hold everybody else if they feel like they're good though.
Yeah, I mean, that's all we have. Do we have any questions on this, you guys? Okay, if you want to stay for more of these, we can. If you feel like you're good and you just want to go and practice this stuff, but go and practice it. Don't just wait till Thursday and think, oh, you know, what? Balancing what? How do balance equation? Practice it, okay? So if you want to leave, I'm not going to feel bad, but anyway, I'm going to do number 1 here. So we got H3PO4 plus potassium hydroxide plus potassium phosphate plus H2O.
So because it has the PO4 put together on both sides, we should just count that as one unit.
That's right. And I'm not going to start there because there's only one on each side, right? Mm-hmm. Thanks. So I'm going to start somewhere else. Where do you want to start?
Thank you.
Thanks. Maybe the potassium, right? Uh-oh.
Oh, but
I should have put an arrow right here. Whoops. Okay. I'm going to start with potassium. Why not hydrogen? Hydrogen has 3.
it has,
Because it's everywhere.
ah,
Right? There's 2 places that has it on this side, so let's save it for last, right? So I have 3 potassiums on the right. So what number do I put there? A 3. So now I have 3 potassiums on the left. And now I can try, do we have hydroxide on the right? Doesn't look like it. Now I got to count the oxygens anyway, right?
so we can't do the.
You can, just don't. I'm going to show you something else that might be cool. If you don't like this, then don't do it. Can we change water to be HOH?
I suppose we could, it wouldn't be.
It's the same, right?
Yeah,
So we have hydrogens and hydroxides. You don't have to do that.
I feel like I would lose a lot of things doing that.
Okay, then let's not. Let's not.
It's very easy to pull a fast one
Mhm.
like that.
Okay. So let's save, and I'm not going to count this oxygen over here and over here with this one. I'm just going to count these 2. I have 3 oxygens there, and so I better put a 3 right there.
Yeah.
You with me? And now phosphates are good. Now we can do hydrogens. Which side should we do? The side with the most. We have 3 here and 3 here. That's 6. And we have how many there?
3,
Times 2 is
6.
6.
Oh, so it's balanced.
Oh, it's all balanced. Not too bad, right?
Yeah.
And could we have counted every element singly? We could have.
It would have taken forever though.
A little bit longer, right? But we have time. No big deal. So do it whatever way makes most sense and this fits to your brain, right?
Okay.
Any other questions?
No, I think, yeah.
Okay, go home and practice this stuff. You have the answers on the back. Go practice it. Are we good, Eric? Okay.